Hi, my name is Alan Vigan, and today I'm going to talk about how to explain some strange behavior of leaky A0 lamb waves at low frequencies. I'll start off by giving some context. Free lamb waves are exact solutions for plates immersed in a vacuum, and if you put that plate inside a fluid, then the surface vibrations on the plate will push and pull on the fluid, causing pressure waves in the fluid. And in the other direction, the fluid will be loading the vibration, thus affecting it. And then the plate will have a solution called leaky lamb waves, which is an exact solution for the fluid immersed plate, which takes into account how the vibration radiates waves into the fluid, and also how the vibration is attenuated due to the power that is radiated away. Now let's look at a concrete example where we have a 1 millimeter thick aluminum plate in a vacuum, and on that plate we have an A0 wave, which is a kind of flexural wave, a bending wave. And waves like this at low frequencies are strongly dispersive. Unlike every other type of lamb mode, their phase speed actually goes to 0 with the frequency. Now what happens if we change the vacuum to air? Well, first of all, we can see what goes on at low frequencies for the free plate in the vacuum. It has phase speed like this, going down to 0. It has no attenuation because there's no fluid for it to radiate into. But if we look back at the phase speed, at some point, which is called coincidence, it's going to cross the speed of sound in the fluid. And if you look up any acoustics textbook dealing with this, it'll tell you that above this coincidence, you will get a radiating wave into the fluid, whereas here below coincidence, you're going to get a non-radiating evanescent wave. So immersing this plate into air, we see first of all that the A0 mode stops roughly at coincidence. But one strange thing is that it goes actually slightly below coincidence. You can see that there is some radiation going on even below the point of coincidence. So that's the first strange behavior that we'll be looking at in this talk. Then if we artificially increase the density of air further, we can see that this effect becomes stronger. There is radiation even further below coincidence. Increasing it further, we see another strange behavior, namely that the A0 mode starts reappearing at low frequencies. So not only does it disappear, but it reappears at very low frequencies. And as we compress it further, we see that the two ends where it disappears and then reappears, they get closer and closer together until eventually the mode doesn't actually disappear at all. So that's the third strange behavior that we're looking at here. There are also a few things to note here. There is not just nothing between the two ends of these A0 modes. There is actually a loop of two different modes that are non-leaky that connect the two ends of the A0. We're not going to go into that in this talk. Also, one reason why we chose this particular case is that we are reproducing an article from '96, which is one of the first ones to point out this phenomenon. There's also a very good article from 2006, which showed that any A0 will have a loop like this if the fluid density is below a certain threshold. But that's a very mathematically oriented article. It doesn't try to give a physical explanation. There's also, as you can see in these results, another mode, a non-leaky quasi-Scholte mode, but we're not going to go into that in this talk. What we will go into is that we will show that all of these strange behaviors follow from the same sound radiation principles. The key to understanding these strange behaviors is to get a better model for sound radiation. Earlier this year we published an article in the Journal of Sound and Vibration investigating such a model. One weakness of classical sound radiation models is that they don't take into account how the surface vibration is attenuated due to the power radiated away by the sound wave. Let's see how much that can matter by comparing an unattenuated and an attenuated surface vibration. These are their pressure fields. So the attenuated vibration creates an inhomogeneous pressure field, where the amplitude changes exponentially along each wavefront. Let's make the attenuation a bit less exaggerated, and then we can look at what happens as the vibration speed decreases towards the fluid's sound speed towards coincidence. As we cross coincidence, the wave on the left will make a jump as it becomes evanescent. For the wave on the right, however, there is no such transition. Attenuated surface vibrations always create a radiating inhomogeneous wave. To build a better radiation model, for example for this case of a Lamb wave in a plate, we need to take two quantities into account. The first one is the power flow along the plate, px. The second one is the intensity radiated by the sound wave into the fluid, IRAD. Note, by the way, that we have a color coding here. Things that deal with the plate and the vibration are printed in blue. Things dealing with the sound wave and the radiated power are printed in orange. So to have conservation of energy here, we need to make sure that the radiated power into the fluid is equal to the power lost from the vibration in the plate. And this actually directly gives us an enhanced radiation model, which is like an implicit equation for the attenuation, kxi, as a function of the amplitude of radiated power and the amplitude of the power flow. Further, we can express this radiation model as a function that must be equal to 0. We can normalize that function by inserting for the amplitude of the radiated intensity, normalize with a wave number k. And this gives us a normalized radiation model where the equation is only a function of components of the wave number, except for this factor c, which we call the radiation factor. That is a function of things to do with the fluid or the wave, in orange here, and in blue, the squared magnitude of the surface vibration and the amplitude of the power flow. This model gives us a particular behavior where we have a radiating wave in the supersonic domain here, and this extends into the subsonic domain for a while. And in the subsonic domain we also find an evanescent wave, which is what we expect from the classical model as well. The magnitude of C also determines not just how strong the radiation is, but also how far it goes into the subsonic domain. Let's look at some power balance examples. In the supersonic domain, there's only one energy-conserving solution where the radiated power balances the vibration's power loss. This solution is a radiated wave. Just below coincidence, there are two energy-conserving solutions. There's an evanescent wave and a radiating wave. Further down below coincidence, there's only one valid solution, namely the evanescent wave. Now this explains the first strange behavior that we identified. Taking the attenuation of the vibration properly into account shows that energy-conserving subsonic radiation is possible. Next, let's look at the importance of the radiation factor C from our radiation model. But first, let's define the cutoff phase speed. This is the lowest vibrational phase speed that supports a radiating wave for any given radiation factor C. Now, let's look at what happens as we follow an A0 Lamb wave down with frequency. We start above coincidence with a radiating wave, and at coincidence we still have a radiating inhomogeneous wave. Same below coincidence. But notice that as we go down in frequency, the radiation factor C increases. And as it increases, the cutoff phase speed, the end of the black line, goes down, and the current phase speed in yellow has to catch up with it, which it does at the start of this loop. Now let's skip to the end of the loop. At this point, the radiation factor C has increased so fast that the cutoff phase speed has caught up with the actual phase speed, which again enables a radiating mode. And as we keep going down in frequency, C increases so fast that the cutoff phase speed outruns the actual phase speed. Now this explains the second strange behavior of the reappearance of the A0 mode. Because C increases so fast with decreasing frequency, the cutoff phase speed will eventually catch up to and outrun the current phase speed. Finally, let's look at the third strange behavior, where the A0 wave never cuts off if the fluid is dense enough. Here we see that the current phase speed never actually reaches the cutoff phase speed. Hence the explanation is that C now is high enough and increases so fast that we never actually reach cutoff. Another way to look at this is through the cutoff radiation factor. For a given phase speed, this is the lowest radiation factor that supports a radiating wave. For air, the radiation factor C hits cutoff just below coincidence, but as we artificially increase the density, and hence C, we find that the radiation factor eventually increases enough that we never hit cutoff. So to summarize, we have explained these three strange behaviors purely from radiation principles without having to dive into the physics of leaky Lamb waves. First, we can get radiation in the subsonic domain, because energy-conserving subsonic radiation is possible, as the enhanced radiation model shows. Second, the A0 wave reappears at low frequencies when the radiation factor has increased so much that energy-conserving subsonic radiation becomes possible again. Third, the A0 wave never disappears for heavy fluid loading, because C is then so high that the energy-conserving subsonic radiation never becomes impossible. Finally, thank you very much for listening. If you found this talk interesting and would like to know more, I highly encourage you to check out our article from Journal of Sound and Vibration from earlier this year. And also I would like to encourage you to look at the various other references that our work is based on, which you can find also further down on this list. Thank you again.